This video is sponsored by PCBWay. Hello there and welcome back to another video. It's been quite a while since I've posted, and that's because I've been working on a very big project that I've finally completed with the release of this video. So, in today's video, I'm going to be working on my newly refined version of my DIY power supply tester project. And guess what? This one has all files, schematics, and tutorials available so you can build it yourself. Let's jump right into this project by walking through a bit of my design process. With my first version of this project, there were several things that I wasn't really happy about. Firstly, there were a few incorrectly wired things that had to be rewired in weird ways, and secondly, the way that it drew power from the power supply when placing a load on it was something that I'd call anything but elegant. Those were the two main items that I wanted to fix, the wiring errors that I made originally, and the loading circuitry. However, there are a few other goals that I want to set as well, namely higher accuracy, measurements of more voltage rails, ripple measurements, and power supply spec detection, as well as some more advanced failure detection and classification. Some of these issues are to be addressed in the software part of the project, but there are several that need to be addressed with the hardware, so let's start there. I began the project by seeking out the exact Molex connectors that mate with standard PC power supply cables, as I didn't love the use of cable extensions in the previous design. This took annoyingly long, but eventually I had the motherboard 24-pin connector, CPU 8-pin connector, and PCI Express 8-pin connector in the schematic with matching footprints attached. I also added a footprint for some 5-pin connector with the idea that you can use that footprint to attach a pigtail with either a SATA or Molex power connector on it, for the sake of testing peripheral power cables. The next thing that I jumped to designing was the new and improved loading circuitry. In the previous design, I just used some large power resistors to draw approximately 1 ampere from each rail of the power supply. This time, I chose a more precise, compact, and adjustable method, constant current loads. These are very simple circuits consisting of an op-amp, a MOSFET, and a few passive components. And these allow you to set an amount of current that you want to draw from the source, and then the circuit will use its inbuilt feedback loop to draw that exact amount of current from the source no matter the voltage. Besides that reason, there are a couple more reasons that this way of loading the power supply will be massively better than the previously used method. First of all, this will largely reduce the size of the power resistors in the load circuitry. There will still be power resistors, but each one will be a little less than half the size of each power resistor that was used in the old design, and furthermore, there will only be one resistor per loaded rail. In the previous design, there was sometimes more than one resistor per rail to get the loading right without having to buy a ton of different value power resistors. Next, the heat dissipation of the load will now be able to be relocated to a heatsink more easily. This is because in the new circuitry, the majority of the power is not dissipated through the resistors and is instead dissipated through the MOSFETs. This means that I can easily group all the heat together into a singular place that's easy for the user to monitor, rather than having some hotspot resistors when the rest are pretty cold and having them spread out all across the board. I set the amount of current to be drawn by the loads with a voltage divider, which provides a voltage reference to the non-inverting input of each op-amp. Then, the inverting input is hooked up for feedback, and the output drives the MOSFET. I'll be toggling the loads by cutting or supplying power to the voltage dividers, and these dividers are calculated to provide about 1.2 volts as the op-amp's reference voltage. Because in this case, a 1 ohm resistor is being used in the loading circuit to generate the feedback voltage based on how much current is going through that resistor, 1 volt on the non-inverting input of the op-amp will drive the load to draw 1 amp of current. So these loads will be drawing about 1.2 amps from every rail of the power supply, except negative 12 volts, as that rail both seems like it will be hard to get working cleanly, and also isn't that important a rail to have on the loads for testing. Even though negative 12 volts is the only rail that won't be loaded by the tester, it's still a rail that will be measuring, as it's an important rail to be able to confirm functional. However, the microcontroller that I based this new design on, initially, is the ESP32, and the ESP32's ADCs, or analog to digital converters, which we use to measure voltage, aren't designed to take a negative input voltage. So I'm going to need to flip this voltage to a positive voltage that corresponds to the negative voltage. And while I'm at it, I need to reduce it from a max of 12 volts to a max of 3 volts. Otherwise, it will fry the 0 to 3 volt rated ADCs of the ESP32. Thankfully, I was very easily able to run across this design online that does everything I need it to do. This is an inverting amplifier circuit, and for this case, it will work flawlessly. This circuit uses an op-amp and 2 resistors to invert the input voltage with a gain value that is specified by the resistor values. Then, after the output of the circuit is measured, as long as the values of the 2 resistors are known, you can calculate the voltage that is being fed into the circuit with a simple equation. This circuit isn't technically perfect and does have its limitations, most of which are related to the specs of the exact op-amp you choose, but in this case, an LM35A op-amp should be sufficiently accurate. Conveniently, this is also the exact same op-amp as is used in the loading circuitry. I did some simple math and settled on a resistor value of 5.6 kiloohms for Rin and a value of 1 kiloohm for Rf. These things are pretty much the most important parts of the new design compared to the old one, at least in terms of hardware. After all of this was sketched up in my software, I went on to set up the voltage dividers for measuring all the non-negative voltage rails, and then I wired up the ESP32 microcontroller to buttons, LEDs, a screen, and the rest of the tester's circuitry. I also added in a 5-volt voltage regulator to provide a 5-volt rail for some parts of the circuitry, as well as the microcontroller. Before I move on to some prototype testing that I did for my load circuitry and the inverting amplifier circuit, I want to draw a little bit of attention to one of the pins on the ESP32. This pin here is being used as a sense pin to determine whether or not a PCI Express connector is plugged into the tester. The old tester had no way of knowing this, and so when determining whether or not the unit passed or failed each spec, there had to be 2 ATX specs. ATX and ATX without PCI Express, which I think is just dumb and can be massively improved in this new design. So I disconnected one of the ground pins of the PCI Express connector and hooked it up to this pin of the microcontroller. I then added a pull-up resistor. Don't worry, I switched the voltage to 3.3 volts when I later caught that mistake, and this means that when no PCI Express cable is plugged in, this pin will read as high or 1. Then, when a PCI Express cable is plugged in, the pin will be connected to ground through the common ground within the power supply, and the pin will switch to reading low or 0. This allows the tester to decide whether or not it needs to be concerned if PCI Express voltage is present. If an ATX power supply is connected to the tester and there's no PCI Express cable connected, it shouldn't fail the unit for there being no PCI Express voltage present. At this point, I was ready to push the project to a PCB. But before doing that, I needed to verify the functionality of 2 parts of this circuit, the inverting amplifier and the small transistor network I constructed to toggle the loads on and off. After putting together the inverting amplifier on a breadboard, I hooked up my voltmeter to its output and connected a negative 12 volt source to its input with one of my bench power supplies. With negative 12 volts on the amplifier's input, the output was sitting at around 2.1 volts. This is exactly what I should be seeing with the resistor values that I chose, and after pulling up a calculator and double checking this, the output of the amplifier is off by only 0.04 volts compared to what the calculator says it should be outputting. However, all resistors have a tolerance, basically a percentage that they are allowed to be off from their marketed value to still be sold as that value. This is almost certainly the cause of the 0.04 volt discrepancy between the calculated voltage I should be getting and the measured voltage that I am getting. And if I was to plug in the exact values of these 2 resistors, I should get a pretty much spot-on voltage. Alright, so that circuit is good, but what about the load toggling circuit? Well, I built it up initially, but was running into issues getting my load to draw the amount of current that it was supposed to from the power supply, so I ended up going on a tangent about fixing the load circuitry itself first, rather than testing the toggle circuitry. To cut a medium-length story short, it turned out that because of the way that this exact circuit works, in particular, the mode that the MOSFET is operating in, 5 volts is not enough voltage to be providing to its gate. Usually, 5 volts is sufficient with these IRF-Z44N MOSFETs for a simplistic switching application, but this application is slightly different, and will require more voltage at the MOSFET's gate to drive it enough to pass 1.2 amps of current. I found out that powering the MOSFET's gate directly off the 9 volt battery that will supply the tester with its power works well, meaning that the op amps in the load circuitry need to be on the 9-volt rail rather than the 5-volt rail. A simple enough fix. After getting the load working, I built up my small transistor network for toggling the load and found that it worked flawlessly, as I figured it should, but it's still good to double check. And with that, I pushed the project out of Fusion 360 and into KiCad because Fusion was having some issues with this PCB, and designed the PCB for this project. Sadly, I can't show any of this footage because I have no idea where all 250 gigabytes of those screen recordings went. Not sure how I misplaced that massive of a chunk of footage, but you know what, it doesn't matter, because the PCBs are here now and we can build this thing. I got these PCBs for this project from PCBWay, the sponsor of today's video. PCBWay is a company that provides high-quality custom manufacturing processes, including but not limited to 3D printing in several different materials, CNC machining with support for, again, a ton of different materials, and also PCB manufacturing. Last month, PCBWay was celebrating its 10th anniversary, but they've extended their celebrations all the way through the month of August, so you can still join in on the fun. During this celebration, they're giving out all kinds of exclusive coupons, and there are some other fun activities you can participate in as well. These activities include the 10th anniversary badge charity sale, marking your location on the globe and sharing your experience with PCBWay, and participating in the lucky draw to win some cool prizes. Check out PCBWay at the link in the video description. Back to the project at hand, I received my PCBs along with some parts for an upcoming video, stay tuned for that, and after taking them out of their package and inspecting them, they look perfect. I spent a lot of time designing this PCB to be as friendly a PCB to put components on as possible, both for me and those of you who choose to build this project yourselves, as no one enjoys having to reference a schematic for every single resistor and transistor value. I also stayed away from being exceptionally heavy on SMD parts, as I didn't want to make this a nightmare to solder. That being said, I still did use a lot of SMD resistors for the sake of keeping the PCB a reasonable size. All of the SMD resistors are in the 0805 package, and I used hand solder friendly footprints for all of them so that you should be able to solder these to the board with just a soldering iron, solder, flux, and some tweezers. You can also get by without any magnification, and I soldered a few of these resistors with no magnification just to prove that it's totally doable. However, I do own a microscope for soldering, so I'm going to switch over to that for the rest of the SMD soldering, as it's easier and allows me to get better footage. I went through soldering all of the SMD resistors to the board, of which there are quite a few. However, when I came to resistors 35 and 36, which are the resistors involved in the inverting amplifier circuit, I chose to measure the exact two resistors that I'd be soldering on the board with a multimeter before soldering them on. This is a little bit tricky with these SMD resistors, but you only have to do it twice for these two resistors. The other ones you'll have to measure are all through hole and should be an easier job. I wrote the measured values down and saved those for later, as they'll be important when coming to the software section. You can also skip this step, but do be aware that your negative 12 volt rails voltage measurement will probably be reasonably inaccurate. Something that the keen-eyed among you might be wondering at this point is why didn't I use a single master voltage divider to provide the 1.2 volt reference signal to the load circuit op amps? This would have saved a lot of resistors, so why didn't I do it? Well, the reason that I didn't do this is because I didn't design that part of the circuit very efficiently, but the reason that I've come up with after the fact so that I don't have to go back and fix it is so that you can change out those resistor values to draw different amounts of current from each rail. I'd go easy on scaling up the current draw too much, as I didn't design the traces in this board to handle much more than 1.5 amps. However, if you do really want to scale up the current draw, you can order the board as a 2 ounce per foot squared copper board and maybe get around 2 amps max out of each trace, which is about as much as you should be drawing, as the heatsink built into this design is less of a heatsink and more of a thermal mass to buy runtime of the load. Pumping tons of watts into that piece of aluminum will lower the amount of time the load can be turned on massively. With all of that said, if you want to lower current draw on any of the rails in particular, you can go as low as you want by changing these resistor values. After all of the SMD components were soldered to the board, I moved on to soldering most of the through-hole components. There are a few through-hole components that will need some extra things done with them before we solder them down though, so don't immediately jump in and solder everything. What I did is solder all of the components except for the through-hole resistors, as those are the components that are going to need that extra work. However, before I get to those, there are a few other through-hole components that I should make a few notes on here. one of which is the connector that I designed to be able to accept most of Dell's small form factor power supplies that use the 8-pin motherboard connector. It turns out that I wired up this connector slightly wrong, and so if I was to solder it to the front of the board, the pinouts would be all wrong and it just wouldn't work. However, if I soldered it to the back of the board, it works perfectly, and I also think that it works better like this due to how short the motherboard cable is on most of these small form factor Dell power supplies. I then soldered on the microcontroller's female headers and the IRF Z44N MOSFETs for the load circuitry. These MOSFETs get soldered to the back of the board so that they can connect to the aluminum heatsink, which should be located right where your hand wants to grab the tester. This is by design so that you can constantly monitor the temperature of the load and turn it off when it gets hot. Do be careful though, because certain parts of the load will get hotter than others, and this load will get hot enough to burn you if you let it get too hot. So just watch its temperature, and once it's not comfortable to hold in your hand anymore, it's time to turn it off. The heatsink for this load will be fashioned out of a 3/4 inch by 3/4 inch square bar of aluminum. When making the heatsink and installing it onto the tester, it's pretty important to have the MOSFETs as straight as possible and evenly aligned in terms of height, so keep that in mind when soldering them down. Now that all of that's said, it's time to work on the through-hole resistors that make up the voltage dividers in this tester. These step the voltages of the power supply's rails down to voltages that won't overload the analog to digital converters of the microcontroller. Then, the microcontroller can measure the proportionally steps down voltage, and with the known values of the two resistors in each voltage divider, can solve for the voltage that's coming into the voltage divider from the power supply. Knowing the exact values of these resistors in each voltage divider is critical to having an accurate final voltage readout. Tolerances of these resistors are enough to throw these values off significantly, which was partly observed in the testing of the inverting amplifier circuit. So, when putting together the voltage dividers on this project, you need to use a multimeter to measure the exact value of each resistor before you put it into the board. Then, after you have its value and have placed it into the board, mark down the component label that corresponds to the resistor you just measured and installed. For example, I measured the value of this 10 kilo ohm resistor at 9.97 kilo ohms and then inserted it into the place for R40. Now I have the resistor in its spot, ready to be soldered, and have written down on the note that R40 measures at 9.97 kilo ohms on this board. You need to do this for all 18 resistors in this section. After all the voltage dividers were done, the last thing I did was solder the 9-volt battery clip onto the board, and with that, the board is complete. The next thing I moved on to was creating the heatsink for the load MOSFETs, and this part is absolutely necessary, as without this added thermal mass, the MOSFETs will nearly immediately overheat. I made this heatsink out of a 3/4 inch by 3/4 inch square aluminum bar, as mentioned earlier. I began by marking off an 8 cm length of the bar and cutting it off with a hacksaw. However, I might advise against making yours exactly in this order, as it can be easier to drill the holes we'll need to drill when you have the whole rest of the bar to hold onto with a vise or something. So I might cut it last if I were you. In any case, I cut off my 8 cm length and then drew a line along its length approximately 5 mm away from one of the edges of the bar. This will be the vertical level of all the holes that would be drilled for mounting the MOSFETs. Then I placed the bar in between all 9 MOSFETs and marked about where the center of the holes in the 5 MOSFETs on the side with 5 MOSFETs were. All of this while making sure not to move the bar itself much, of course, just to not throw off the spacing. Since the 4 MOSFETs on the other side should be directly opposite of the ones on the side we based the markings off of, there's no need to mark those MOSFETs with drill locations. Then, I transferred the center locations of each hole down onto the line I marked earlier to give me 5 drill locations. The next step is to drill either 3mm or 1/8 inch holes all the way through the bar in each of these marked locations. Be certain to keep the holes 100% straight, otherwise the heatsink will not work. If you have a drill press, use it. I promise it will make your life so much easier during this part. But if you're like me and don't have a drill press, I used one of these little drill guide things, a vise, and some clamps to make each hole. It took me 2 tries in the end and was quite hard work, but eventually I got one that was decently accurate. I actually ended up making the diameter of my drilled holes a bit larger than an 1/8 inch because not everything was perfectly matched up dimension-wise, and having some wiggle room was helpful to make the heatsink fit. Also, make sure to file down all sharp edges from cutting the bar, and I used a large drill bit to take out the burrs on the holes. Lastly, I mounted the heatsink to the MOSFETs using one M3x25 screw for the singular MOSFET and 4 M3x30 screws for the other 8 MOSFETs. It's absolutely critical to use proper isolation pads and bushings when doing this, otherwise you'll merge all of the power supply's rails together, and that will be a very bad time. Each MOSFET needs a pad and a bushing on it to keep it isolated from both the aluminum block and the M3 screw used to attach them to the block, and you might need to trim the isolation pads slightly depending on the size of the ones you get. Make sure to check that your isolation is good by using a multimeter once everything is mounted. One final thing for this step, I reflowed all of the solder joints for the MOSFETs after I mounted the heatsink, as there was some tension on some of the MOSFETs and I wanted to relieve that from the board as well as the solder joints by reflowing them. Alright, it's finally time to finish off this build, or at least the physical part of it. This is probably the single most simple part of this build, as all I did to wrap this up was 3D print a plastic 9V battery holder and hot glue it to the PCB. I then put some electrical tape inside it to make sure that the 9V friction fitted solidly, and that's it. It's done. I plugged the 9V in and flipped the power switch, and the display came to life with the OLED display test program that I had loaded onto this ESP32 from a prior test. I then jumped into the software world for a solid 15 hours and crafted up the software for this tester. After loading it onto the microcontroller, I plugged the ESP32 back into the board and powered it up to test it. The initial section of the code seemed to be working great, as it prompted me to turn on the power supply to begin the test. And after I pressed the button to do this, the LED indicated that the microcontroller was trying to turn on the power supply, and a second later, the load turned on as well. After a few seconds of testing, the tester informed me that it could not figure out what kind of power supply was attached to it. At this point, there was no power supply attached to it, and because of this, the PSU had failed catastrophically, which I'd consider to be accurate, considering that there is no power supply. I could press the menu button to view the voltage measurements and the ripple measurements, and at this point, I was ready to plug a power supply in. After plugging in an old ATX power supply, I began the testing process. However, the tester failed the power supply, which it shouldn't have, because this power supply is known to be good. It failed with a complete voltage failure, which is also wrong, so I turned the power supply back on and went to look at the voltages that the tester was measuring. This is when I discovered that it was measuring the voltages of all the rails to be very low, registering as low as 10.87 volts on the CPU 12V rail, a measurement that's absolutely inaccurate. I then took my multimeter out to check the CPU 12V measurement that we should be getting and found that the tester should be displaying a voltage of 11.84 volts, almost a whole volt off from what my tester was saying. When measuring some of the other rails, such as the motherboard's 5V rail, I found that they were also incredibly off from the actual voltages that the power supply was putting out. Now I had to figure out exactly what the problem with the voltage measurement chain was, as the results are so inaccurate it's completely skewing whether or not the power supply fails, something that is completely unacceptable. Since this video is already getting really long, I'm going to cut this part short. I troubleshooted this for a solid 2 days, but didn't get the tester accurate enough to the point where I liked the measurements it was giving. This is because it turns out that the ESP32 was probably the single worst microcontroller I could have chosen for this job. This is because it's known for having an inherently flawed ADC. It turns out that the ESP32's ADCs are just known to be inaccurate, and I tried several different methods of compensating for this, including implementing some curves to the voltages to try and match the non-linearity of the ADCs, and I even experimented with some code for calibrating it. But all of this failed to get the measurements accurate enough to where I was happy. The methods I tried to use to fix this seemed to consistently get the ESP32's ADCs within a 1% margin of error. Sadly, it turns out that 1% of 12 volts is still 0.12 volts, and that's a pretty massive amount of possible error for something that's supposed to accurately measure voltages. So, as much as I wanted to keep this project more inexpensive and simpler by using an ESP32, I found that I had to use a different microcontroller to get accurate readings. And the only other one I have that will fit the bill for this board is the Teensy 4.1. The Teensy 4.1 is an absolutely amazing microcontroller. It's got an insanely powerful CPU, lots of I/O, and 12-bit ADCs that are accurate. It does feel like a bit of a waste of the CPU on the Teensy in this project, but I don't know anything about the STM32 boards, and therefore don't want to use one here until I know what I'm doing with them. So now, the solution is to retrofit a Teensy onto this board. But before I made an adapter PCB that will allow me to plug the Teensy into the ESP32 socket, I wanted to ensure that the Teensy would do what I need it to do, and I did this by creating a tentacle monster. Don't laugh, this works. This thing worked massively better than the ESP32 did in terms of accuracy. However, it was still a bit off, which I found odd. It was off by about 0.9 volts, which is still in the unacceptable region for me. However, since I know that the ADCs should be good this time, the resistor values for the calculations are accurate, and there shouldn't be anything else interfering, I decided to see if I could fix this slight inaccuracy with a curve of some sort. So, for each channel, I went through injecting voltages from 1 volt to 13 volts, and I wrote down the difference in voltage between my multimeter and the tester at each voltage. After this, I had a table of voltages and their corresponding discrepancies between the two measurement apparatuses. I then plugged this into Desmos and performed a simple linear regression, as I found that this fit the plotted dots the best. I then used this equation in the code to curve the voltage readings for each channel, and every channel got its own curve because they all acted slightly differently, and with that done, the tester was accurate to a T throughout the whole range of voltages. So now that the Teensy was confirmed to be a microcontroller I could trust to give accurate readings, even if it needed a little bit of help, I went back to KiCad to draw something up. Then I headed back over to PCBWay to get some more PCBs, which will allow me to plug my Teensy 4.1 into my board's ESP32 socket. In the version of this board that I'll be releasing to you, I'm just putting the Teensy directly onto the main PCB, so this is a board that only I'll need for my version here. But anyway, I soldered up one of these little boards, plugged the Teensy into the Teensy socket on it, and then plugged the Teensy conversion board and Teensy into the ESP32 socket. After all this was done, I turned on the tester, and it worked exactly as it should, except for the fact that once again, the voltage readings were inaccurate. However, this time, the voltage readings the tester was giving were higher than the actual voltage that was being fed into the tester. They were also higher by a suspiciously similar amount to the amount of voltage that the curve should be adding. Sure enough, after removing the curves, the Teensy started spitting out nearly spot-on voltage readings, with at most 0.01 volts of error, just as it should be. It seems like my octopus of wires was causing the Teensy to register voltages as lower than they actually were for whatever reason, and my best guess is due to some higher resistance contacts on some of the lines. So, with the tester's voltage reading functionality figured out, I gave it some tests to make sure that all of its features, such as spec and failure detection, seemed to be mostly functional, and they were. I didn't simulate every single type of failure for every single type of power supply to test it out, because that would have taken a long time, and all of the detection is based on the same simple code structure, and the couple that I did check worked great. However, when I went to test a Corsair power supply that has a PCI Express cable, I ran into yet another issue. I had been looking at the Dell ATX power supply during the design process and missed that this Corsair power supply has these annoying pieces of plastic on the sides of its connectors that make my right angle connectors unusable, as the power supply cables don't fit with the PCB right there. This was really frustrating to me, but I'll get around this issue by using some cable extensions to test the unit when I eventually pick some up. Don't worry though, this issue has also been fixed in the PCB that I'm providing to you all, so you shouldn't have to worry about this. To test the PCI Express cable detection though, I used a PCI Express extension to make a dummy PCIe power cable that should trigger the PCI Express sensing circuit, just like a power supply would, and that I could also inject 12 volts into to test the voltage measurements. Thankfully, both of those parts of the tester worked great, and I think that finally this project is wrapped up. Though this project wasn't perfectly smooth for me, it should be much smoother for you if you choose to build it for yourself. The design that I've been working on in this video is a V2, but the flaws that I discovered when making this version 2 have enabled me to make a version 2.1, which is mostly identical to this, but with the few discovered kinks worked out. Version 2.1 is the version that will be available to you through the PCBWay shared project and instructable below. And if you think this would be a fun project to make, I encourage you to check them out. Do know that this isn't a project for someone who wants a super simple power supply tester that's cheap and easy. This is a project for someone who wants a power supply tester, but also loves to build things themselves and enjoys a good project. Before I end the video, let me do a quick rundown of the features on this new power supply tester. I didn't do a full walkthrough this time like I did on the old tester because this one is much more feature packed, so I'm just quickly going to run through the features in this voiceover so that you can have an idea of what this tester does. This tester is built to take 3 types of power supply: an ATX power supply, an ATX power supply with a PCI Express cable, and a Dell small form factor power supply. The tester will automatically figure out what kind of power supply you've plugged into it based on a sensing probe for PCI Express cables, as well as several set parameters that should accurately discern between an ATX power supply without PCI Express power and a Dell small form factor power supply. If it cannot confidently figure out what kind of power supply is connected to it, it tells you that and fails the unit. It will still allow you to power on the unit, load, and view voltages as well as ripple measurements at this point, just as with any unit that fails for any reason. Another design choice that I made with this tester is the removal of the ability to perform an unloaded power supply test. I didn't really see the purpose of testing your power supply without a load, especially with this tester, and just didn't want to program that functionality. When testing the power supply, the unit gets turned on a second before the load to give the power supply a little bit of breathing room before it gets hit with a 60-ish watt load. Additionally, the functionality that ensures the rails of the power supply all stay consistent across the 3 voltage samples taken during the test is still implemented. If any inconsistency is found, the unit fails. Moving on to one of my favorite things about this tester is that it provides a failure reason when a unit fails rather than just telling you that it failed and leaving it at that. For example, I tested this feature by leaving the CPU cable unplugged from the tester when testing this power supply, and it failed the unit with a CPU voltage failure message. That pretty much wraps up the major features and functionality of this tester, or at least the stuff that I'll be going over on video here. If you want some more details, I'll have a more comprehensive user's guide on the Instructable in the video description. Well, that's all that I have for you today. I hope that you were able to at least enjoy this video and maybe even learn a thing or two. In any case, I hope to see you next time, this time with less of a gap between videos. Goodbye.